generator terms in powers of another. We want to take care of the behavior of the minimal generators of powers of monomial numbers. This study is based on two of my joint papers, a different which I made up. With field and x being the polynomial names in the variables x1 up to xn over the field k. And we can have be the unique graded maximum ideal of S. And let I be a graded ideal here. By graded ideal, we mean an ideal generated by homogeneous polynomials. A homogeneous polynomial is a polynomial generated in S. For such an ideal, there will be a set of minimal generators. Of course, that is not unique in the case of monomial ideal, it's unique, but in the case of other graded ideals could be maybe it's not unique, but the cardinality of this set is unique, which we call the minimum number of generators of I when we denote it by mu of I. Right? So mu of I is the minimum number of generators of I. So if we consider this function f of k to be mu of ik, for a graded ideal I, then this is the Hilbert function of the fiber cone of I. The fiber cone of I is by definition this one, and the Hilbert function is just the dimension of these components. In each point is the dimension of this component as a Hilbert space. And there is a famous theorem by Hilbert, which says any Hilbert function of a finitely generated graded module is in a polynomial type. That means from a certain point on, for enough large case, it's a polynomial. You can find this theorem everywhere, especially here. I don't know. You can find it in this book here, in the list. This is the famous theorem of Hilbert, which says is the Hilbert function of a finitely generated graded R module is of polynomial type. That means from a certain point on, for enough large powers, it's just a polynomial. Okay, let's go back to our story. Is not a okay, now since this guy is the Hilbert function of this K algebra, so we can say that f of k, which is mu of ik, is a polynomial for enough large powers of k. Okay, and in particular, this implies that if I is not a principal ideal, which means if I is generated by more than one element, then mu of ik is strictly less than mu of ik plus 1. That is, mu of ik after that point, after this enough large k, is strictly increasing function, right? Now, why? Because this is a polynomial which positive with a positive leading coefficient. And for enough large case, this gives us this condition, which is strictly increasing. But the very general question is, what is the behavior of the function u of ik before this point? Before this enough large k, what will be the behavior? For example, can we say it is still increasing function? Of course, when I am not principal, when I is principal, we have nothing to do because the same. So, if the answer was yes, we have nothing to do. So, always push this.
Oh, it's okay.
Okay. So, in the case that I is equigenerated and equigenerated graded ideal, and equigenerated, we mean an ideal generated in a single domain. All the generators have the same domain. Is that problem? No, yeah. Did I continue? Okay. So, if I is an equigenerated graded ideal, so there is a theorem by Herzog, Mohammad and Zamani that says yes. The answer is yes. That is strictly increasing function before this point as well. And this follows from celebrated theorem in number theory by Freeman. But and especially in the case that I is a monomial ideal. A monomial ideal is a generated ideal with just one component, right? So if we generated monomial ideal, even there is a lower bound for the minimum number of generators of IK. So you can find, and this is done by Herzog, Hibik, and June, and you can find the theorem in this paper, which is published in the prestigious journal Maxima, and this is the theorem. Even they proved the theorem for quasi-equigenerator. We don't care for the moment for quasi-equigenerator, but an equigenerated monomial ideal is a particular kind of quasi-equigenerator. And this is the lower bound. If you check, even the lower bound is increasing. As if you consider the lower bound as a function, k it is increasing. It is not easy to check, so it is not clear, but you can check. So, if that means if you want to look for an ideal such that the function is not increasing before this is large power k, we should look for an ideal. Analytic spread is just the crude dimension of the fiber. Okay. But at this moment, we just care about the behavior. But this is an invariant, right? Yeah. But it means if we want to look for ideal with different behavior, we should look for an ideal which is not generated in a single degree. And there are some examples. For example, Eliyahu, Herzog, and Mohammad provided some monomial ideals such that mu of I squared is strictly less than mu of I. And you can find it in this paper. which is published in the Journal of Algebra, and you can find it as this theorem. They show that if the mu of I is at least 5, then there exists a monomial ideal such that mu of I is m, and mu of I squared is none for any m bigger than or equal to. For example, if you have, if you consider, for example, for 100, you can find an ideal such that mu of I is 100, but mu of I squared is only 9. And they showed that if m is bigger than or equal to, greater than or equal to 6, and this is the best case. That means mu of I squared never will be less than 9. And this is short. Okay. And also Casanova provided some examples such that for any even number k, mu of ik less than mu of I. And this is published here, but it is not just a theorem, it is one section of this short paper. It's a kind of procedure. But mu of ik is just less than mu of I, not less than mu of ik minus 1 or ik minus 2. Just this one. And now, so these are two different examples for behavior, for the initial behavior of mu of ik. Now, our main question is how wild the initial behavior of mu of ik could be for a monomial ideal. For example, can we have local maxima, maximum, or local minimum, and how many can goes up and down or not? This is a very general question that we consider, and as an overview to what we will discuss, the first part of the talk will be based on my paper with Herzog and Zarin Andy, and the second part with my paper with Shinya Komashiro. And first, for the first part, you can find the paper here, my paper with Herzog and Zarin Andy. So. Let's do some construction. We fix some integers. We fix an integer n, which is at least 1, a at least 3, and we set n to be 2. That means number of variables are 2, right? This is 2, right? And we consider this ideal. J is x1 to the power an, x2 to the power an, multiplied by this ideal. x1 to the power n, x2 to the power n. And we let, as usual, n to be the graded maximum ideal of the unique graded maximum ideal of S. And for that fixed a and m, we denote this ideal by I and m, which is j plus m to the power c. And what is c? C is d plus n minus 1, and d is the degree of the elements of this monomial. Okay? So the degree of generators is a plus m, we call it d, and our c is d plus this c plus m minus 1. And we set our I to be j plus m to the power c. But as you see this ideal is not generated in a single degree anymore, right? Because C is strictly bigger than D. Okay. So why we consider this? This is a long procedure. We use the second degree of this ideal J, and we had like an interval of alternatives for this C. But this was the best case for our goal, and then we choose this one. But we skip that part. We just go through the results. Okay, now we have this proposition. Mu of this side, this guy, and this one. For the powers less than or equal to a minus 1 is this guy, which is a parabola. And after this point is just a line. It's a linear function. And will be strictly increasing, right? But this is a parabola. Right? So that means for the, this is an integer function, but for the moment I assume it as a term. For example, if this is A, the form of the behavior was like this until this point. Okay, and from this point on is just a line. But this is just an integer function. Right? This and so on. So you see, there is a parabola and then a line. Okay. Now we can prove that if we consider A to be at least 3 and M enough large, this point is a local maxima here. And what is this point? It is the root of this fraction. By the root, we mean the nearest integer to this fraction, right? Because this is an integer function, and we need an integer. So this point is the local maximum of this integer function. Okay, so if you ask me, if you give me a number, I can provide you an ideal such that in that number, in that particular power, has a local maximum, right? As well as if you give me another number, I can provide an ideal with a local minimum in that particular point. For the first one, this one, and for the second one, this one is that one. For example, if we consider our A to be a 4 and our M to be this guy, and if you check by formula, we have mu of I is 24, mu of I is 29, and here again goes down, right? And at this point, we have a local maximum, right? Again, from this point on, is that a linear function? Just this is plus 1, right? From this point on, again, is a linear function. So if you want to try for others, for example, okay, I need 1 minute to try some other examples. Okay, let me write the code for this one using Cocoa. We let our we need to define our local, our maximal ideal, and I will be ideal. Let's first try this one, x to the power 40, y to the power 40, multiplied by the ideal, sorry, ideal x to the power 10, y to the power 10. Then we look for, sorry, and here I add my power of m, and we look for the powers, the minimal generators of powers. From 1 to, for example, let's add for 6, for example. Let me find them in new lines. And 4. I hope everything is fine. Something is wrong here for 2 here. Let me just you see, ideas 24, 29, 16, and for this one is just medium. And now this is just for when you have when you ask for power a local maximum in power 2, right? So if I want to try another one, for example, for a local maximum in power 3, I should take my A. Okay, according to the last corollary, the middle point of that interval was the best case for a local maximum. So I need to the powers for the power 3. I need to take A to be 6, and M enough large. I will try 15. Then I write 90. Again 90, and this one 15, and this one 15, and D plus M minus 1 would be 119. And now I hope 15 is enough large. Okay, yes. You see, here again, we have the local maximum in the circle, right? We just need to find suitable A and enough larger, right? Oh, okay, let's go back to our slides. Okay. Now we have the local maximum in N on W. Now the next step is that we want to look, we will look for more local maxima. Is it possible to have more than one? We say yes. Consider the same ideal, but several times in different base rings, and such that these polynomial rings, the set of variables are pairwise disjoint. X1, Y1, X2, Y2, and XL, YL. And we set I to be the product of these ideals, right? And for any J from 1 to this number N, we had the formula for these guys, right? We had the relation for mu of IK, which was this one. But if we consider particular choices like MJ to be A and AJ to be J, right? Then we will have I is this guy, and the mu will be this. Okay, this problem. Okay, we think if we just substituting this guy and this guy here, and then we will see this guy. Now, mu of IK is this one. In each interval, the relation is in the particular thing. For the first one, comes from these intervals for each of them, the product of these polynomials for each of them. For the next one, for one of them comes from here, for the last one, for the rest comes from here, and so on. Why it's like this? Because the variables are pairwise disjoint, right? The base sheet. And for this particular idea, we could prove that for any given Q, using this ideal, this kind of ideals, we can provide an ideal such that it has the function mu of I has at least Q local mass, at least Q, not exactly Q, right? For example, if we consider A to be 20 and L to be 14, then the idea will be this, and the procedure guarantees at least 3 local maxima, because there will be 3 intervals here, and then in each interval we prove that there is 1 local maxima at least. But this is at least. Indeed, for example, in this case, it has really 8 local maxima. But the story goes that it's 3 out. Okay, I'm done with this part. And the next part is some ideals which the function for them, the function of k, which is mu of ik, is extremely increasing up to any arbitrary power k, right? And this is based on my joint work with Shinya Kamashiro, and it is published in the article. If we consider S, the ideal, the polynomial in 2 variables, x1 and x2, and ideal ring, monomial ideal, as we already mentioned, these 3 people gave these sharp lower bound, right? But if mu of I is at least 6. And also Casanova could provide this kind of ideals. ideal with this property, that mu of ik is strictly less than mu of I. But now, in some, we generalize those results. We can prove that for any positive integer R, there exists a monomial ideal satisfying these conditions. Mu of ik is strictly decreasing up to the power k. Up to the power r. And from this point on is strictly increasing as a line, as a linear function, right? Okay, you see, this is in this sense, this lower bound is 2 plus 1 squared, right? And our result takes r plus 1 squared. In that sense, is generalization of that result. And here, mu of ik is just strictly less than mu of I, but here, mu of ik is extremely the linear function. Each step up to this point is increasing. And it is like this. Come down, maybe up as a line, up from this point on here, and increase. And how we could provide this kind of ideals? We assume these integers f, P1 to Pn, A2 to An, all of them should be at least 2. And we set this kind of ideals. I1 is this one, and for other i's, I should say j. Ij is this guys. And we set I to the sum of these guys, these ideals. And we set some particular conditions on these integers. We choose P1 such that for all j between 2 and n, P1 is aj plus 1 times pj. And also P1, the sum of P1, P2 to Pn minus 1 should be strictly less than P1. Then the powers of these ideals up till this point is this guy, and from this point on is just the base power of I1, right? So as you see, in each step up till here, in each step, one of these guys disappears, right? One of these, when k is increasing, then one of these guys will disappear. Like in the second power, this one disappears. In the third power, another one, and at this point, just remain this one. And from this point on, it's always these guys are always equal, right? And mu of this ik until this point is this guy, and from this point on, again is a line, right? As an example, if you consider these numbers, they satisfy that condition, these conditions. And because I to be this, then we have, but for these ij's, is just what we define here. What we define here. And if you check it, you see that it's decreasing until this point, power 5, right? And in power 5 is just 5 plus 1 squared, right? And from this point on, then is linear. Exactly what we have here. What we have here. Okay, now the last part of this part, we want to provide an important application of our story here. There is an important invariant in commutative algebra. It's called Cohen-Macaulay type. Cohen-Macaulay type of an R module, of a ring, or an R module. And that is important for several reasons. For example, if you have it is somehow measurement of complexity of in structure is a construction of the module or the ring, especially regarding the canonical module of that ring. In particular, if you have a Cohen-Macaulay then if this Cohen-Macaulay type is 1, the Cohen-Macaulay ring will be Bornstein. And also in algebraic geometry is a kind of measure for complexity of the singularity of algebraic varieties. The higher Cohen-Macaulay type means the more complex singularity, which means worst case. But also, we can interpret it as the index of reducibility of braided modules. Index of reducibility means the number of components that appear in an irredundant or reducible decomposition of a module, a braided module. And especially for monomial ideal is exactly that one. So now what we have here, we could prove that, these three guys, Goy and Chu, showed that if we consider Cohen-Macaulay type of this particular module as a function in K, then again, this is a polynomial from a certain point, right? But again, we can ask this question: what will be the behavior of this particular function for small forms? Here is their paper, and here is the theorem. They show that for enough large K, it's a polynomial, but for a particular case, we prove that if R is a two-dimensional regular local ring, and I is an ideal of an improbable ideal of R, then mu of IK is the Cohen-Macaulay type of R over IK plus 1. The index of reducibility of this plus 1. And this is an important result, and especially in the case of the polynomial rings in two variables, that helps it. Because there is a well-known decomposition for the irredundant irreducible decomposition of monomial ideals in two variables. Okay, again, that this also works for that local maximum point and the local minimum point. But particularly related to this paper, we have these results. If we consider these three, and ideal, and primary ideal, then we have if the polynomial type of S over Ri is at least 5, then the sharp lower bound of the polynomial for the second power is at least 8. This follows what's from the theorem of Tensor. And this one is following from our last theorem that the polynomial type is strictly increasing. There are some ideals, but polynomial type is strictly increasing up till a certain, right? So I think we are done. These are some references we use. My two papers is people and the paper of Corey and Strong, the paper of Young and so on side, the paper of Casanova, and so division. And this was the last one is what motivated us for starting this story. And I appreciate your attention.